Welcome to this essential training video focused on designing machine learning systems that are robust and reliable. We will explore what reliability means in the context of ML, identify common system faults, and learn key strategies for implementing fault tolerance. Let's get started. Welcome to this training video on reliability and fault tolerance in ML workflows. When we talk about machine learning, or ML, in a production setting meaning systems that real users depend on, we are dealing with highly complex structures. These ML systems involve many components like data pipelines, specialized algorithms, infrastructure, and business goals. For any ML system to be successful in the real world, it must satisfy four key requirements: reliability, scalability, maintainability, and adaptability. Today, we focus on reliability. Reliability is the capacity of your ML system to consistently perform its intended, correct function at the expected speed, even when things go wrong, such as hardware failure or a bug in the code. This is crucial because ML systems often suffer from a unique and dangerous problem: silent failure. This means the system appears to be operating normally, no crashes or error codes, but it is silently delivering completely wrong predictions, potentially causing harm or misleading users. In the next slides, we will explore what causes these faults and how to design systems that tolerate them. This diagram visualizes the primary requirements for production ML systems, highlighting reliability. Reliability is just one of four critical characteristics, alongside scalability, maintainability, and adaptability. Reliability is fundamentally determined by two checks. First, whether the system meets its operational expectations, like speed, and second, whether its core predictions are accurate and correct. If either of these expectations are consistently violated, you have a system failure. Crucially, the system can suffer a failure even if operational metrics are green, because the predictions might be silently wrong. This need for continuous prediction correctness is what makes reliability in ML unique and challenging, demanding advanced fault tolerance mechanisms beyond what traditional software often requires. We are focusing on preventing these internal failures from impacting users. What have we learned? We learned that reliability in ML goes beyond just keeping the system running. It demands that the system's predictions are consistently correct. This prepares us to explore the common causes of incorrectness, or faults, in the next slide. As we discussed, reliability in ML systems has two parts: meeting operational goals and achieving high prediction performance. Operational expectations are common to all software, covering things like how fast the system responds, called latency, and how many requests it can handle per second, called throughput. The ML performance metrics, like accuracy or F1 score, measure how good the predictions are. The real difficulty lies in establishing correctness. Even if the system successfully executes the function to generate a prediction, the prediction itself might be fundamentally wrong, yet the system gives no indication of failure. This is the silent failure mode. For instance, a translation service might return a grammatically correct sentence, but the meaning is entirely wrong, and the user won't know the system failed. We must design our systems to detect and prevent these subtle, dangerous failures, which are much harder to spot than a traditional software crash. This flowchart illustrates the difference between silent and operational failures. When a request is sent, if the system crashes or throws an error code, that is a loud operational failure. However, the silent failure path is much more deceptive. The ML system is running. The prediction function executes successfully, but the resulting prediction is incorrect. Since no system crash occurred, the wrong output is simply delivered to the user or downstream service, as if it were accurate. Preventing this silent failure requires continuous monitoring of prediction quality, which is fundamentally different from just monitoring if the servers are up. This concept of checking prediction correctness is essential for true ML system reliability, moving us toward effective fault tolerance. What important point did we cover? Silent failures are the critical difference between reliability in ML and traditional software. The model might technically run, but the output could be garbage. Next, we explore the primary causes of these failures in production. ML systems often fail due to three major, unique reasons. The first, and arguably most pervasive, is the data distribution shift. Your model learns from a finite training set, but real-world data is constantly changing and often messy. If the unseen production data diverges from the initial training data, perhaps due to new feature encoding or seasonal trends, the model won't generalize well, causing a train-serving skew. The second source of failure involves edge cases. These are inputs that are so rare or unusual that the model never learned how to handle them during training. While small in number, failure on an edge case like an unusual street sign for an autonomous vehicle can have catastrophic, life-altering consequences. Finally, degenerate feedback loops happen when a model's own output influences its future input. For example, if a recommender system only suggests popular videos, users will only watch those videos, reinforcing the system's bias toward popularity and making other content invisible. This mind map shows the three primary types of ML-specific failures. First, we have issues related to the mismatch between production and training data, commonly called train-serving skew. This is rooted in data distribution shifts, which includes label shift, covariate shift, and concept drift, where the relationship between inputs and outputs changes over time. Second, edge cases represent rare situations where high accuracy is crucial but hard to guarantee, demanding specialized attention. Third, degenerate feedback loops highlight system design flaws, where the model unintentionally biases its own future data inputs, leading to narrow, homogeneous results. True fault tolerance involves anticipating and mitigating all three of these complex failure modes. What have we learned? The reliability of ML systems is threatened by data-related issues, data shifts, rare edge cases, and self-reinforcing feedback loops. This leads us directly to the first major mitigation strategy: ensuring data consistency across the entire workflow. Since data is the foundation of ML failures, fault tolerance must start with maintaining data consistency. In many production systems, two different pipelines handle data. The training pipeline processes large amounts of static, historical data in batches. The inference pipeline processes small amounts of live, streaming data for real-time predictions. Using separate systems to extract features in these two pipelines is a primary cause of bugs, resulting in feature inconsistency and the critical train-serving skew. For example, an engineer might calculate a feature differently in Python for training versus in Java for production, leading to different inputs. To achieve fault tolerance, these pipelines must be unified, ensuring that features are computed exactly the same way for both training and serving. Specialized tools called feature stores help solve this by managing consistent feature definitions, accessible across all stages, whether for batch historical training or real-time prediction. This diagram shows the crucial role of unified pipelines in achieving fault tolerance. Traditionally, training uses historical data processed in batches to create batch features, while inference uses live, streaming data processed continuously to create streaming features. The core challenge is that if the processes, batch processing and stream processing, are implemented separately, the resulting feature sets often become inconsistent, leading to the dangerous train-serving skew. To tolerate this fault, modern ML system design leverages tools like a feature store. The feature store acts as a centralized component, ensuring that features used in the batch pipeline and the features used in the inference pipeline are mathematically identical, thus eliminating inconsistencies and improving reliability. What important concept did we discuss? Feature consistency across the training and inference pipelines is fundamental for reliable ML systems, often requiring the use of tools like a feature store. Next, we look at mitigating specific prediction faults like edge cases and feedback loops. To ensure reliability, our model must be robust against specific prediction faults like edge cases and feedback loops. Edge cases present a high risk. Even if they happen rarely, their consequences can be catastrophic. Fault tolerance here means dedicating significant time and resources to rigorously test these specific scenarios until the model handles them safely. For degenerate feedback loops, where the model keeps recommending what is already popular, we combat this homogeneity by adding randomization. For example, a video platform might intentionally show a small portion of users' random, unproven videos. The resulting user engagement provides unbiased data, preventing the model from getting stuck in a popularity-only loop. Furthermore, models like transformers process data in parallel, losing natural sequence information. We introduce positional features explicitly, encoding the order of data points, to recover this crucial information, ensuring robust and accurate processing. This diagram illustrates the relationship between specific ML faults and their necessary tolerance methods. Edge cases, characterized by their rarity and potential for catastrophic failure, are primarily mitigated through specialized and rigorous testing. Degenerate feedback loops, which introduce self-reinforcing bias, are addressed through strategic prediction randomization. This means deliberately exploring non-preferred options to gather new, unbiased data, which breaks the reinforcing cycle. Finally, modern architectures, particularly those using parallel processing, risk losing crucial sequential information. Positional features or embeddings are engineered specifically to overcome this, explicitly feeding location information back into the model to maintain context and improve robustness. What have we learned? Randomization is a powerful fault tolerance technique to fight self-reinforcing biases in ML systems by forcing the model to explore new possibilities and collect unbiased data. Our next step in achieving reliability is through robust monitoring. Monitoring is the critical infrastructure component for achieving fault tolerance. Since silent failures and data shifts are pervasive, you cannot rely on manual checks. Monitoring tracks two classes of metrics: operational metrics, which confirm the hardware and software systems are healthy, and ML-specific metrics, which confirm the predictions are healthy. ML-specific monitoring should track 4 key artifacts across the data pipeline. These are the raw inputs, the data coming in, the features, the processed data used by the model, the predictions, the immediate output of the model, and finally, the accuracy of the predictions if the correct labels are available. Monitoring inputs and features is particularly valuable for fault tolerance, because deviations here are fundamental and often indicate a major data distribution shift, the root cause of many silent failures. This graph illustrates the flow of artifacts monitored in a reliable ML system. Data starts as raw inputs, is transformed into features, results in predictions, and, if natural labels exist, can lead to accuracy metrics. All these artifacts must be continuously tracked by the monitoring infrastructure. Critically, monitoring inputs and features is fundamentally harder because they are less structured, but changes detected at these early stages provide powerful warnings of deep-seated data distribution shifts. Changes in raw inputs or features often signal a fundamental shift in the underlying data probability distribution, such as covariate shift, which is less likely to be caused by simple human error further downstream. Monitoring is a passive form of fault tolerance. It alerts you to the problem, but it only detects the problem, it doesn't fix it automatically. What important point did we cover? Monitoring the entire ML pipeline, especially upstream at the raw input and feature stages, is essential for detecting the subtle data distribution shifts that cause unreliable predictions. Next, we examine how the development process itself can promote reliability. Building a reliable ML system is not a single, linear task. It is an iterative cycle. This cycle ensures that once a fault or poor performance is detected during monitoring, you quickly circle back to refine the project scope, improve the data, or adjust the model. For effective fault tolerance, the guiding design philosophy should be simplicity. The Zen of Python principle, simple is better than complex, applies strongly to ML systems. Start by implementing the simplest possible solution first, even a non-ML heuristic or a simple linear model. Simple models are easier to deploy, which validates your prediction pipeline early on, and they are significantly easier to debug when silent failures inevitably happen. Crucially, the simplest model provides a vital baseline performance that all subsequent, more complex models must beat to justify their added complexity and potential for new faults. This diagram shows the iterative cycle of ML system development, crucial for embedding reliability and fault tolerance. The process starts with defining goals, moves through data preparation, model training, and deployment. The critical step is monitoring and continual learning. When monitoring detects a fault or performance drop, the system iterates. Faults lead back to data engineering, step 2, for cleanup or new labeling, and performance analysis informs business analysis, step 6, which may refine the initial scope, step 1. This continuous feedback loop ensures the system adapts to shifts and actively fixes newly identified faults, rather than letting the system degrade over time. Simple models facilitate this iteration, as they are faster to deploy and analyze. What have we learned? Designing for reliability starts by embracing the iterative cycle and adhering to simplicity, using the simplest algorithm as an initial baseline for comparison and easier debugging. Our final step is integrating adaptability through continual learning. We conclude our journey with the ultimate form of fault tolerance, adaptability. Adaptability means the system can cope with continuous changes in data and requirements. Since data distribution shifts are inevitable and constant, the most robust solution is continual learning. This practice involves actively updating the deployed model with small batches of new, incoming production data. However, updates must be safe. We achieve this using the champion/challenger process. The deployed model, the champion, stays running and reliable. A replica, the challenger, is trained on new data. The challenger is rigorously evaluated against the champion on a real-world test set. Only if the challenger proves significantly better is it promoted to replace the champion. Otherwise, it is discarded. This ensures that our systems are not only robust to current faults, but are constantly adapting to future faults and changes, maximizing long-term reliability. This diagram depicts the continual learning cycle, a robust pattern for achieving adaptability and fault tolerance in ML systems. The system always maintains a reliable champion model in production. New incoming data is collected in micro-batches and used to train a replica called the challenger. The challenger is then evaluated against the champion, using real-world metrics. If the challenger shows improved performance and safety, it is deployed to replace the champion, completing the cycle and ensuring the system adapts to changes. If the champion is superior, the challenger is simply discarded. This iterative and tested approach prevents catastrophic forgetting and maximizes the system's ability to maintain high reliability over time, ensuring that prediction quality keeps up with evolving data distributions. What have we learned? Continual learning using the champion/challenger approach is the key to achieving long-term fault tolerance, allowing the system to safely and automatically adapt to the constant data distribution shifts characteristic of the real world.